Okay, thanks for the introduction. And it's my honor today to introduce my recent work with my postdoc advisors, Yang Kim and Jeffrey Schiebinger. And here's the problem setup. Since I only have 10 minutes, I have to assume everyone is super familiar with this entropic optimal transport. And we have a density evolution rho t where the time t ranges from 0 to 1. And for simplicity, we also assume everything is on the flat torus TD. And we're interested in this entropic optimal transport problem. And we consider its primal form to minimize such loss functional. And the cost function C epsilon here, the K epsilon is the heat kernel on the flat torus. So we know on the Euclidean space, this heat kernel is just the density function of the Gaussian distribution. So this cost function reduces to this quadratic loss on the Euclidean case. And for this Cal divergence regularization part, there is a coefficient epsilon which decreases to 0 when this EOT epsilon, this epsilon decreases to 0. And we know there is some duality theory of this entropic optimal transport. So it can also be written as a maximization problem over the space of functions. And this is the loss function for this dual form. And today we are interested in this problem. So think if phi t epsilon and psi t epsilon are the Schrodinger potentials for this EOT problem. And when epsilon decreases to 0, we would like to ask if this phi t epsilon and psi t epsilon allows some Taylor expansion with respect to this regularization coefficient epsilon. And we study this problem simply motivated by the stability of multi-marginal Schrodinger bridge problem. So now we are given two density flows, rho mu and rho nu. And also we are given a few time points from 0 to 1. And usually this density evolution is induced by a stochastic process. But in practice, we cannot observe anything of this stochastic process. So people try to understand such process by using this multi-marginal Schrodinger bridges defined by minimizing this Cal divergence with such marginal constraints. And in practice, we can observe such like marginal constraints of the stochastic process, but there are usually some noises. And assume there was some like noise perturbation on these observed marginals from this rho mu to rho nu. And we are interested in how this perturbation on the marginal distributions propagates to the Schrodinger potentials, to the Schrodinger bridges. And this perturbation of the Schrodinger bridges can actually be, say, characterized using this Cal divergence, which is defined as the integration of the Rn derivative of these two solutions. And here, W is the distribution of the standard Brownian motion on the flat torus. And I would like to emphasize both this W and this solution of the Schrodinger bridges are the measures on the path space rather than just the ambient space flat torus. And we want to find an upper bound characterizing the stability that where the leading term only depends on the perturbation of marginals plus a high order term that decreases to 0 when the number of time points m goes to infinity.
I have typo there. I think you have typo there.
No.
Log. You forgot log.
Okay. Oh, you're so right.
Yeah, okay.
Yeah. Thank you. And we know that this multi-marginal Schrodinger bridge have the so-called Markov property, which basically says it can be decomposed into a few two marginal entropic optimal transport problem. And for each part, we just need to solve an entropic optimal transport problem to get the optimal coupling, and then connect the optimal coupling using the Brownian bridges. And assume we have such Schrodinger potentials for each flow in each piece. And then we can rewrite this Cal divergence using the Schrodinger potentials as this equation. So it is natural to think that we can control the difference of the Schrodinger potentials by using some stability result of entropic optimal transport. And in fact, there is one from Carlier, Chizet, and Laborde in 2024, which says this perturbation of Schrodinger potentials in CK norm can actually bounded by a constant multiply the perturbation of marginal distributions. And this perturbation is characterized in the W2 distance. But the problem is there is a constant before this W2 distance. And think if we have m time points from 0 to 1, and they're generally uniformly sampled. So for 2 consecutive time points, the difference should be at the order of this 1 over m. And when we take this order on this exponential term, we see a constant depending on m at the order of e of m, which clearly explodes when the number of time points m goes to infinity. And we want to solve such a problem. So we can rewrite this Cal divergence into another form. And again, we see this 1 over the time gap is at the order of OM. And we also have a summation here. So this shaded part actually provides an OM square order thing. This somehow suggests that if we can expand this Schrodinger potential in second order, then we can characterize all the leading term, where the rest of part just corresponds to the high order term that decreases to 0 when the number of time points increases. So I think this problem well motivates the reason we want to study this Schrodinger Taylor expansion of Schrodinger potentials when the regularization coefficient decreases to 0. And here's the intuitive derivation of the Taylor expansion. And I would like to emphasize that the coefficients here should be functions rather than some constants. And we know that the Schrodinger potentials satisfy the so-called Schrodinger system. And it can be like we have 2 equations in this Schrodinger system, and one of this look at the first part of this equation. And since we also have the connection between this cost function and the heat kernel on the flat torus, so we can take this C epsilon, the cost function here, and write this integration into the convolution of the heat kernel and this multiplication. And to decouple this convolution, we take the Fourier transform motivated by Morden's paper in 2024, where this paper only considers they have the same marginal constraints, but here we have like different marginal constraints. But anyway, this Gaussian convolution, this heat kernel turns into this exponential term. For the other 2 terms, it just turns to its Fourier transform. And assume everything is good enough, then we can do a Taylor expansion for this exponential term, like the exponential of this Schrodinger potentials into this infinitely many terms. And also we can expand this exponential term in epsilon into a polynomial with infinitely many order terms. In this case, both the left-hand side and the right-hand side turns to be polynomials in epsilon where there were like infinitely many order terms. And then we can compare the coefficients on the left-hand side and right-hand side to get like infinitely many PDEs with respect to this coefficient functions UK and VK. So we can solve all of these PDEs to get all these coefficients and get the expansion of the exponential of Schrodinger potentials and take the log, multiply epsilon on both sides to get the Taylor expansion of the Schrodinger potentials when epsilon decreases to 0. But previously, we assumed everything is good enough and we can do the expansion for the exponential of Schrodinger potentials. And here we formalize this idea, which basically says if you want to do a capital K order Taylor expansion, then both the Schrodinger potentials phi and psi allows the kth order expansion. And the error in L2 norm is at the order of epsilon k plus 1 as expected. And again, since we are motivated by the stability of multi-marginal Schrodinger bridges, and there we say we're more interested in the first order 2 expansion. Here, I just provide the first order expansion for simplicity. And if this rho T satisfies such continuity equation, and with this velocity vector field, then the first order expansion actually is related to this velocity potential and the log of the density evolution at this point. And this theorem is proved under these two assumptions. The first one basically says the density evolution is bounded from above and also below away from zero. And the second one says the density evolution is super smooth. And actually, if we are only interested in a capital Kth order expansion for the Schrodinger potentials, we do not need this infinitely order smoothness, but just a finite order smoothness that is proportional to the expansion order capital K. And I think this is all of my today's presentation. And also I would like to advertise myself. Yeah, I'm on the job market this year looking for jobs in math, statistics, and data science. Yeah, thank you.